So let's move on to the third talk of this session. It's by Gil Salgado, and he's going to talk about contact and Frobenius Lie algebras. Thank you.
Well, I must thanks to the organizing committee for inviting me. Special thanks to Ivan Kaigorodov for his kind invitation to talk in this simple school. I will talk about contact and Frobenius Lie algebras. Almost all I will say is a joint work with Maria Alejandra Alvarez, Maria Carmen Rodriguez Vallarte, and two undergraduate students, Trino Barajas and Manuel Roque. So let me start with the double extension process by Professor Katz. As the name say, we need to do two steps. The first one, start with the algebra. I will assume that the ground field are or the real numbers or the complex numbers. We need a close to form theta or a two cycle. That is the same name. We need a one-dimensional vector space. In this case, the generator is named as E. And then we need to construct the direct sum of the original Lie algebra and the one-dimensional vector space. And then we can define a new Lie bracket using the close to form in this way. If we take two elements in the original Lie algebra, we add a multiple of the generator to the original Lie bracket G, and any element of G will commute with the new element. And this is a new Lie algebra known as the central extension of G by theta. And this element, this new element, belongs to the center of the central extension. Okay. In this, as a second step, we need a derivation in the central extension of the Lie algebra. And a derivation is a linear map satisfying the Leibniz rule. And we must construct a semi-direct product of this abelian one-dimensional Lie algebra with the central extension. And now the Lie bracket is defined by these two rules, because we have two vector spaces here. In particular, if we take the derivation and any element of the central extension, we only need to value the derivation in the element. Well, this new Lie algebra will be denoted as G of D and theta, and will be called the double extension of G by D and theta. Okay. In each step, we have a kind of control in the following sense. Two central extensions given by alpha and beta will be isomorphic if and only if their cohomology classes are the same in the scalar 2 cohomology of G. And if we extend the Lie algebra by a derivation, and I will denote as G of D, two of these kind of extensions will be isomorphic if and only if there exists a non-zero scalar, an element on the Lie algebra, an automorphism of the Lie algebra, and if we can describe the first derivation in terms of these operations. However, the bad news is that there are non-isomorphic Lie algebras in such a way that the double extension process produces isomorphic Lie algebras. So this is not as good as we want. Okay, now let me talk about quadratic Lie algebras. Given a Lie algebra and a symmetric bilinear form B, we say that B is invariant if the following equality holds. And here we are asking for all x, y, and z belongs to the Lie algebra. As usual, the radical of the bilinear form is this subspace, and B is not degenerate if and only if its radical is trivial. Okay, an invariant metric on G is a non-degenerate, invariant, symmetric bilinear form on the Lie algebra. And the pair G and B is a quadratic Lie algebra if and only if B is an invariant metric on G. So let me now talk about symplectic and Frobenius Lie algebras. If we start with an even dimensional Lie algebra and omega is a non-degenerate skew symmetric bilinear form on G, we will say that the pair G omega is a symplectic Lie algebra if omega is closed. Moreover, we will say that the pair is a Frobenius Lie algebra or exact symplectic if there exists one form, in this case denoted by bar phi, such that omega is the exterior derivative of the one form. In this case, we will say that omega is a Kirillov form on G, and by definition, we can compute omega using these equalities. Okay, a contact Lie algebra is an odd dimensional Lie algebra, and we are assuming that there exists one special form, a special one form, bar phi, satisfying that this wedge product is not trivial. There are a lot of contact Lie algebras. The following is a very well-known fact. Take any three-dimensional Lie algebra, non-isomorphic to the abelian three-dimensional Lie algebra, or neither the Lie algebra labeled as Q sub 1, and then G is a contact Lie algebra. So as you can see, almost all three-dimensional Lie algebras are contact Lie algebras. Okay, why we start with the double extension process and quadratic Lie algebras? Well, in 1982, Professor Katz proved the following theorem. If we start with a solvable quadratic Lie algebra, then we have two options. The first one is that G can be decomposed as an orthogonal direct sum of a one-dimensional quadratic ideal and one codimension 1 quadratic ideal. Or if G is indecomposable, then G can be obtained as a double extension of a codimension 2 solvable quadratic Lie algebra. Well, a few years later, in 1985, Alberto Medina and Philippe Rebois generalized this theorem. And they prove that we can delete the condition of G being a solvable Lie algebra. And they prove that if G is an indecomposable quadratic Lie algebra, then G can be obtained as a double extension of a quadratic Lie algebra and a suitable subspace. Obviously, if the original Lie algebra of Medina and Rebois is a solvable quadratic Lie algebra, this suitable subspace is a dimension 1 subspace, and it corresponds to the one-dimensional quadratic ideal on G. Okay. 6 years later, Medina and Rebois prove the same theorem, but now for symplectic Lie algebras. They prove that every symplectic Lie algebra with non-trivial center can be obtained as a double extension of a codimension 2 symplectic Lie algebra. So if the double extension process of vector cuts works well in the quadratic case and in the symplectic case, a natural question is, does the double extension process work in contact case? And the answer is yes. If you start with a finite dimensional contact Lie algebra and take any central extension of G by a 2 cocycle theta and define this element in the dual of the central extensions, taking the original one form of G and a multiple of the dual of this element, if there exists a derivation such that this condition holds, then the double extension of G by D and theta is a contact Lie algebra for almost all elements in the ground field. So when we got this condition, we asked if this is a good condition or not. So can we construct examples in which we can guarantee this condition? Well, the answer is yes. If you take any non-abelian three-dimensional Lie algebra and take any 2 cocycle and take the central extension of G by this theta, then there exists one derivation such that these conditions holds true. In other words, you can implement the double extension process on any non-abelian three-dimensional Lie algebra, and you get a new contact Lie algebra. And if you start with the abelian three-dimensional Lie algebra, then you need to take a non-trivial 2 cocycle, and then there exists one derivation such that this condition holds. And then you can get a new contact Lie algebra. So we got the following. At this moment, this process of double extension allows us to construct a contact Lie algebra if we start with the contact Lie algebra. Allows us to construct a contact Lie algebra starting with a no-contact Lie algebra. And the worst scenario for me, there are contact Lie algebras such that they cannot be constructed as double extension of contact Lie algebras. And I mention this because at the start of this work, we have seen that with the double extension process, we can construct all the contact Lie algebras. And one example of this last statement is the following family of Lie algebras. 5 as subindex is the dimension of this Lie algebra. 35 is the number on the list of classifications, and A and B are parameters in the ground field. Here is the A and here is the B. And this family of Lie algebras are indecomposables. The center is trivial, and all are contact Lie algebras, and we cannot express them as double extensions of a three-dimensional contact Lie algebra. Moreover, we can see that the structure of these Lie algebras are the following. There is an abelian three-dimensional Lie algebra generated by E sub 1, E sub 2, and E sub 3, and a two-dimensional abelian Lie algebra generated by E4 and E5. And the structure is this semi-direct product. And this kind of Lie algebras can be easily generalized to this kind of Lie algebras, and fixing suitable parameters, we can prove exactly the same property. They are indecomposables, trivial center, and they cannot express them, and we cannot express them as double extension of a codimension 2 contact Lie algebras. Okay, in this moment, we ask is there any family in which the double extension process generate all the elements of this family? And well, the answer is yes. We start noting that nilpotent Lie algebras can be constructed as a double extension of a nilpotent Lie algebra and a nilpotent derivation. So with this inspiration, we have proof that if you start with a contact nilpotent Lie algebra, then there exists a contact nilpotent Lie algebra of codimension 2, a 2 cocycle, and 1 nilpotent derivation, and the original contact nilpotent Lie algebra can be expressed as a double extension of the of G, where G is a contact nilpotent Lie algebra, and the contact form can be constructed exactly as before, the original contact form plus a multiple of the dual of the central element in the central extension. And well, as an easy consequence, this theorem say that any contact nilpotent Lie algebra can be obtained for the three-dimensional Heisenberg Lie algebra H3 by applying a finite number of successive series of double extension by pairs d theta, where d is a nilpotent derivation. And as a byproduct of this work, we can give an alternative proof for this known result of Professor Gosse and Rem. Among the nilpotent Lie algebras, the contact Lie algebras are exactly the central extension of a nilpotent symplectic Lie algebras. Okay, now let me talk about Frobenius Lie algebras. We have a Lie algebra, and we are assuming that there exists a one form, bar phi, and the associated Kirillov forms given by this equation is a non-degenerate on G. Obviously, if we have a Frobenius Lie algebra, then the center is trivial, and then there are no nilpotent Frobenius Lie algebras. If you read the work of Medina and Rabois, they ask this condition in the symplectic case between the derivation and the central element. Then they are asking to the central element is central in the double extension. So we ask if this condition is really necessary, and the answer is no. Then, if we start with a Frobenius Lie algebra and take any central extension by a 2 cocycle theta, if there exists a derivation and we got the same condition, we have the same condition, then the double extension is again a Frobenius Lie algebra. So you have noticed, or you can notice that this is the same statement as the previous theorem about contact double extensions. In this condition, for example, is a necessary condition in the quadratic case. And in the symplectic case is not necessary. And obviously in the Frobenius case, it is not possible that this element must be 0. And now let me talk about the relationship between contact and Frobenius Lie algebras. To do this, I need to define two skew symmetric matrices and take a Lie algebra and fix a basis, x1 to xm, and define the matrices as follows. If the dimension is an even number, you define the C of G matrix in this way. And if the dimension is an odd number, you need to add a new row, this one, and a new column, this one, in order to get a new even skew symmetric matrix. And in this case, I will note with the hat. So without hat is dimension even, with hat is dimension odd. And here we must think the entries of these both matrices are elements of the symmetric algebra associated to the Lie algebra. And we are thinking this symmetric algebra as the polynomials in M variables. Okay, in 1980, Professor Ohms proved the following theorem. If you start with a Lie algebra, the following statements are equivalent. G is a Frobenius Lie algebra. We can construct a Pfaffian associated to this skew symmetric matrix, and this element is not 0 element, and there exists a one form such that this matrix is invertible. Recall that the Kirillov form is given by this equation, and this implies that this matrix is the Gram matrix associated to the Kirillov form associated to bar phi. And the Pfaffian of the matrix is the square root of the determinant of the matrix when we are thinking that this determinant is a polynomial in the entries of the matrix. And we need to normalize to get this element as a unique element. Well, moreover, Professor Ohms proved that this element called Pfaffian is a semi-invariant associated to the trace functional, and this means that if you compute this bracket in the universal enveloping algebra of the original Lie algebra, you get the trace in the add of x times the Pfaffian. So he proved that there is no unimodular Frobenius Lie algebras, and unimodular means that the trace of add of x must be equal to 0 for all elements on the Lie algebra. So this element cannot be an invariant because this is not 0. Well, we can prove the same theorem as Professor Ohms. If we start with a Lie algebra, the following statements are equivalent. We have that G is a contact Lie algebra. We can associate a Pfaffian to the hat matrix of G, and this element is not 0, and there exists one form such that this matrix is invertible. Okay, another relationship between contact and Frobenius Lie algebras. In the work of Professor Ohms, they note that as the Kirillov form of a Frobenius Lie algebra is a non-degenerate bilinear form, this allows us to define an isomorphism between the Lie algebra G and its dual. So here in the dual, we have an special element, bar phi, and this is an isomorphism. Then there exists only one element, x sub p, call it the principal element, in such a way that the image, its image by this isomorphism is exactly the one form. This equation, using these two equalities, can be rewritten as this equation. So this derivation follows by the one form is exactly the one form. Okay, and this motivates us to define the concept of principal derivation following the same idea. But now we can start with a contact or Frobenius Lie algebra. So if we have a contact or Frobenius Lie algebra, a derivation is a principal derivation if the same equations holds true. So the composition of the derivation with the one form is the one form. We can denote by their bar phi of G the set of principal derivations. Obviously, this is not a vector space because the derivation zero is not here, because if this derivation zero, this equals to zero. But we see that this set have an affine structure, and the affine structure is given by this decomposition. You need to fix one principal derivation. You need to define this space as the intersection of the set of all derivations on G with all linear transformations sending the Lie algebra into the kernel of bar phi, and this means that these equations holds true, and then the principal derivations is exactly this sum. Okay, why we want to study principal derivations? Another note. 2 or 3 years ago, Giovanni Bazzoni and Juan Carlos Marrero have studied this kind of derivations, and they call it symplectic derivations or contact derivations, because this equation is the same as this equation. Well, if we have a Frobenius Lie algebra, then we can prove that the principal derivation set is not the empty set, but, and this is a bad news, if we start with a contact Lie algebra, then the set of principal derivations can be the empty set. So why do we want to study principal derivations? Well, with 2 undergraduate students here in Mexico, Trino Barajas and Manuel Roque, we have proof that the principal derivations allow us to construct Frobenius Lie algebras if we start with a contact Lie algebras and a principal derivation. And the same holds true if we start with a Frobenius Lie algebra and a principal derivation, then we can construct a new contact Lie algebra. And we are working in this space, in one of the 2 extensions of the double extension process. So we can ask if are they equivalent classes of Lie algebras? And the answer is no. If they are equivalent classes, then all Frobenius Lie algebra must have a codimension 1 contact ideal, and all contact Lie algebra must have a codimension 1 Frobenius ideal, and we know that this is not true. Moreover, if they were equivalent, then we must have that the sets of principal derivation must be not empty, and this is false. We only can prove the following. Every Frobenius Lie algebra can be obtained from a codimension one contact ideal and one principal derivation. So if you can construct all contact Lie algebras, then you can construct all Frobenius Lie algebras. Or if you can classify all contact Lie algebras, then you can classify all Frobenius Lie algebras. Okay, as a final part of this talk, let me talk a little bit more about contact Lie algebras, semi-invariants and invariants. And we can prove that the Pfaffian associated to a contact Lie algebra is again a semi-invariant associated to the trace functional. So satisfies the same equation. And the good news here is that there are unimodular contact Lie algebras. So in this case, the Pfaffian associated to a contact Lie algebra is now an invariant of a Lie algebra. Well, we know that all perfect Lie algebras are unimodular, and by perfect we mean that the first derivative ideal is the Lie algebra, and there are contact perfect Lie algebras. So we can characterize these Lie algebras by the following result. Take any perfect Lie algebra, then G is a contact Lie algebra if and only if its Pfaffian is the only one invariant of G. This result was motivated by this result of Professor Campoamor Sturberg. He characterized the Frobenius Lie algebras as the Lie algebras with no invariant. So you can see that we have a similar result, but we need to assume that the contact Lie algebra is a perfect Lie algebra. Well, I think that is. Thank you very much for your attention. If any wants reference, please drop me a line and I will answer as fast as I read my email, and I will answer. Thank you very much.
Thank you, Gil. Yeah, let us thank Gil for his talk. And if there's any questions or comments, please come forward.
I would like to ask one question, please. What about positive characteristics?
I don't know. I think that's an interesting question, but I don't know the answer. I only work with real numbers and complex numbers.
Mm-hmm. Thank you. Thank you. Yes, it seems really interesting.
Well, thank you.
Please, I have one question.
Yes.
So when I looked at article Frobenius Poisson algebra on the front mat China on 2019 14.2 issue. So they, in definitions 5, they say there is a Frobenius Poisson algebra unimodular. So in your talk, you said there is no Frobenius algebra unimodular. So what do you say about this two sentences in the two articles?
Well, the first one that you mentioned, I don't know.
This article is the title is Frobenius Poisson Algebra on Front Mat China.
Okay.
The authors is Chuan Liu, Wang, and Wu.
Okay.
So
I will read and I will try to answer, but in the Frobenius case, Professor Ohms proved that the trace of the principal element is not zero. So the Frobenius Lie algebra cannot be a unimodular Lie algebra. And he computes explicitly the trace of the add of principal element, and in fact is a half of the dimension of the Lie algebra. So, well, the other work I need to read, and then I maybe can say something. I'm sorry.
Okay. Thank you. Thank you.
No, you're welcome.
Maybe there's someone else who wants to add something to this discussion or ask the question. Christina?
Yes. Hello, Gil. Nice to see you.
Hola.
I want to ask about, you have told that your principal derivations has been studied by Giovanni Bassoni and Moreno
Sí.
from another point of view, and they have called symplectic derivations or something like that. And you have explained a little bit, but well, you were a little fast for me. And I'm interested in knowing their point of view, because they come from another world to us, so they come from geometry. So we would like to know what, why they are studying the same thing.
Okay, yes, in fact, I delete some screens because I don't want to say all that they...
Too much about this.
Yes, they in fact were working in what they call locally symplectic, locally conformal symplectic Lie algebras. And to construct this kind of Lie algebras, they need exactly this kind of derivations. And obviously always exist this kind of derivations. So yes, you can look in the work of Juan Carlos Marrero, and you fastly will find these 2 or 3 works on this direction.
And do you know why are they studying that?
Well, they are geometers. Then they want to construct manifolds with not a symplectic structure, but that they know as locally conformal symplectic structures that is lesser than a symplectic structure.
So there are more symplectic and rigid or something like that.
Yes, yes. If you want, I can write in a few minutes an email with this in Spanish to tell really well.
Spanish. Perfect.
I'm sorry about my English.
The same as the rest, don't worry. Thank you.
Okay, are there any other questions or comments?
Okay,
Doesn't look like-
I would
Yeah, go
like
ahead.
to share my screen.
Mhm. Yeah, doesn't look like there's anything else. So I think we can wrap this up. So let us thank Gil for his talk and also all the other professors who presented in the session. And yeah, I guess we see you all again tomorrow.